Hello everyone and welcome to today's webinar. This session will be split into two main parts. The first part will feature a special presentation on high resolution AFM imaging for polymer science. The second part of the session will feature a detailed demonstration of the Nano platform, where we'll briefly explain what the product is and then go into more of a live demo to show how it can help you and your research efforts. Then following all that, we'll have a Q&A session at the end. Before we get started though, just a quick housekeeping point. All of the attendees on the call are in listen-only mode. So if you'd like to ask any questions, please post them in the chat box and then we'll pick them up at the end of the session. For now though, I'd like to introduce you all to the first of our guest speakers who will handle the presentation on high-resolution AFM imaging for polymers. Dr. Vladimir Korolkov received his PhD in chemistry from Moscow University in 2008. Then he moved to the University of Heidelberg and specialized in X-ray photoelectron spectroscopy of thin films. Following this, he took up a position at the University of Nottingham, where he discovered his passion for scanning probe microscopy and became a strong advocate of SPM techniques to unlock structure and properties at nanoscale. He pioneered the use of higher eigenmodes of standard cantilevers to routinely achieve resolution that was previously thought to be exclusively limited to STM and UHV STM. Vladimir has published more than 40 scientific papers, including 3 in Nature family journals. And he left academia in 2018 to contribute to the industrial side of SPM technology. So Vladimir, over to you.
Thank you very much, Stephen. Thank you for a kind introduction. Good afternoon, everyone, or perhaps a good morning if you're joining us from a sunny West Coast. And thank you very much for joining our webinar about high-resolution imaging of polymers. So in this webinar, we're going to talk about how you can use atomic force microscopy for structural studies of polymers. Specifically, we can look how we can obtain real space and high-resolution images revealing single molecules and how that could help you in understanding the structure of polymers. So the main question is, why do we need AFM? Why do we need another technique to look at the polymers? And there's a number of very good reasons why. First, atomic force microscopy or any scanning probe microscopy in general is the only technique that provides you with a real space imaging, meaning that you can observe individual molecules on both crystalline and amorphous polymers or regions of polymers. That means you can actually see a molecule, and that is really important for chemists because in chemistry, scientists really think about molecules, how to construct materials using these or that molecule, and that actually helps. And historically, that kind of studies were conducted with the diffraction techniques, and you had to use some model to interpret your diffraction patterns and then build a structure. With the AFM-based technique, you can actually get a real space or a real image of your sample. Then another great advantage of atomic force microscopy, it can provide you with the real time and real space dynamics of your polymer samples, meaning that you can actually see a molecule that responds to some external stimuli, be it temperature or some solvent or radiation. So you can see how the molecule diffuses on the surface or in the bulk, how it crystallizes, and so on. Then another important advantage is that atomic force microscopy can provide you with the limitless resolution on almost any scale. You can look at your samples on a millimeter scale or go all the way down and achieve angstrom scale resolution. Then atomic force microscopy in general is damage-free and extremely gentle technique. So you can look at the very hard semi-crystalline polymers, or you can go and look at a very soft biopolymers like DNA or RNA or various other polymers that are typically very soft and they exist in the solution, and yet you will not damage them. And which is quite different to, say, electron-based microscopies, where molecules may be damaged by electron beam or electrons. Then, critically, you can also acquire some properties, or you can perform functional imaging when doing such experiment. For instance, you can collect nanomechanical data, you can probe whether your sample is soft or stiff. You can measure electrical properties, your conductivity, for instance, of your polymer. And you can also do spectroscopic, you can collect infrared data from your polymers. So, and that aspect of imaging will be covered in the following webinar in about a month's time, delivered by Dr. Abdul Rauf. We'll talk about nanomechanical characterization of polymer. So a great question is, so how come having so many advantages, unique advantages, AFM is still not really used for structural studies of polymer? That is a very good question. So today I'm going to show you how we can use a commercial instrument, a large sample atomic force microscope NX20 from Park System, and how that type of system can help you to look at the real-world polymers and resolve their structures. So first, a bit of a brief history in high-resolution imaging of polymers. Perhaps one of the first examples where such imaging was achieved on a routine basis was successful introduction of torsional tapping AFM by Nick Mull and Jamie Hobbs here in the University of Sheffield in the UK, where they pioneered the use of the torsional or T-shaped cantilevers and achieved quite remarkably high resolution images on the polyethylene lamellas in the ambient, and they could image single molecules and critically some molecular defects as well. Then there was introduction of bimodal tapping by Dr. Probst, where they again could resolve individual molecules on the polyethylene lamella. And more recently, there was another version of or some kind of reinvention of tapping mode, is high eigenmode imaging. And that's a technique that I would like to talk a bit in this presentation. Basically, you're all familiar with the tapping mode, where you use quite often the fundamental or the first eigenmode of a cantilever. It's usually that eigenmode or the frequency that is written on the box of your tips. For instance, if you take a standard silicon cantilever like the one we use in this presentation, GIS Multi 75 LG probe, it has a fundamental frequency, fundamental eigenmode of 75 or around about 75 kilohertz. And when you excite cantilever at that frequency, you have a motion as shown here. That's sort of roughly what it looks like. And then you have the amplitude of that motion that is used as your feedback parameter. But that cantilever, apart from the first eigenmode at 75 kilohertz, has another at least four higher eigenmodes. So the second one is at around about 430 kilohertz, and then the third one at 1.2 megahertz. And each of these eigenmodes is characterized by a quite different shape of the cantilever oscillation. For instance, here I tried to show a sketch of a third eigenmode of how the cantilever oscillates when you excite that cantilever at the third eigenmode. It's been shown experimentally when using those high eigenmode, you can achieve basically two important things. You can use extremely low amplitude, something that is almost impossible to use in the ambient with the first eigenmode. You can go down to angstrom level amplitudes or subnanometer level amplitudes, and you can go faster. You can scan faster. So in that way, you can gain the resolution and you can gain the speed. So, and we applied that technique to a range of polymers. For instance, in this presentation, we looked at the Teflon, which is a commercial name for polytetrafluoroethylene. Polytetrafluoroethylene has a remarkably simple structure. So the molecule is made of just two elements, carbon and fluorine, and they form that long chain that can reach the length of tens of nanometers or so. And the polymers is extensively used for all sorts of application, and that's the reason why it has been studied quite extensively as well. But it has been studied only with the diffraction-based techniques. And what people established that it exists in 4 different phases, and the one that is stable at the room temperature, or to be precise, within a temperature range of between 19 and 30 degrees centigrade, it exists in the so-called phase 4, where the crystalline regions of the polymer are made of a hexagonally packed PTFE chains with the chain-to-chain distance of 5.66 angstroms. That number is quite important, so bear this in mind. As I said, the polymer is extremely widely used for all sorts of applications. Just to name a few, for instance, everyone is very well familiar with the Gore-Tex membrane or so-called or expandable PTFE, the polymer that was invented by Bob Gore and used in all sorts of applications, from raincoats to shoes and so on. But the other one product that everyone is very well familiar with is PTFE tape, or plumber's tape, that we use for sealing joints, for insulation, and so on. So that polymer, that sample, we're going to look at today with the AFM, and we'll use that high eigenmode approach to see the structure of the tape and see how the molecules actually pack. So we take literally a piece of polymer that you can buy in any supermarket, put some into a microscope, and perform those experiments in the ambient at 22 degrees centigrade. So first, let's have a look at the large scale. As I said, AFM is unique in the sense that you can look at your samples on almost any scale. Here, for instance, we're taking a 100 micron scan of a polymer surface. But you can multiply 100 micron scan and stitch them together and build a millimeter size picture, for instance. But even here on a 100 micron scan, you can see a very rich, detail-rich image of areas with a dense sort of structure and some rope-like structure that connect them. Equally, you can see the same sort of information in the phase image. We can probably agree that most of the crystalline and semi-crystalline areas are located within these dense areas. So if we zoom, for instance, into one of those and acquire some phase images, we indeed can get an extremely detailed picture that shows quite a few details. For instance, on a slightly high resolution image, we can see a crystalline area where you can see lines running in one direction, in the same direction, in fact, that the tape is oriented. And these lines are, as we see later, they are correspond to the direction of molecules as well. But at the same time, we can equally see a very good resolution on the amorphous region that connects those crystalline regions. But what we really want to have a look at, we want to look at the detailed structure on those crystalline areas. For instance, here in the area that is highlighted with the red square, we will try to observe a bit more detailed structure. For instance, when we zoom in and take a 100 nanometer scan height image, you can see those individual lamellas with a very well-defined steps, for instance here. And when we zoom further into the sort of that small portion of the image and acquire a phase image, we can see that there is a very nice fine structure to this lamellas, and you can see lines that are running along those lamellas. And when we take a cross section and measure the distance between those lines, it is actually 5.6 angstroms. If you remember, I showed you diffraction data on the slide 3, and that data showed a very good actual agreement with the diffraction data. So it's exactly the same number we acquired on the real piece of polymer in the ambient with the atomic force microscope. For instance, on the image C, you can clearly see individual molecules. You can even overlay a model of the PTFE chain. That gives you an idea of how the molecules are oriented. They're basically stretched all the way. So in that sense, that approach, that high eigenmode approach of using a high eigenmode standard cantilever provides you with a really high resolution images on the real world polymer, relatively easy. And the other question, which is quite interesting in the structure studies of polymer, how different parts of those lamellas are oriented on top of each other. For instance, if we take another phase image in a different area of the same sample, we can see nice lamellas, and in fact, you can almost make the lines that are running on the lamella structure, and with the cross section taken across one of those lamella, you can measure again the same periodicity of 5.6 angstroms. But what is interesting is this region where we can actually image the edge of the lamella, and we can see PTFE chains coming off the lamella, and we resolve those individual ends here. And then underneath there is a second lamella that the top one sits on. So the step the step here is actually corresponding to a single molecule. And then the question is, what's the orientation of the top line molecules versus the one at the bottom? So if we take a slightly closer look at the two edges of the two lamellas, and we overlay blue lines on top of the molecules that form the top lamella with the red lines that basically correspond to the molecules on the bottom lamella, we can clearly see that those molecules are interdigitated, meaning that the top molecules are shifted by just one molecule when one lamella forms on top of the other. Of course, there are many other questions remain unanswered. For instance, what's the conformation of the individual molecule within the lamella? That would require additional experiments and so on. But in principle, using that approach, using the high eigenmodes of a standard cantilever, we can resolve single PTFE molecules on a real-world polymer sample on our Park System NX20 AFM. We can achieve true molecular resolution, and in fact we can achieve it on both the crystalline part of the polymer on the lamellas and on the amorphous region, because we can see how those molecules that go into amorphous region, how they form some kind of structure there. And what is critical, the measured molecule-to-molecule distance of 5.6 angstrom is in a perfect agreement with the previous studies that have been conducted on various X-ray diffractometers. So I hope that gives you a sense of confidence that you can actually use atomic force microscopy for high-resolution studies of polymers, of the real-world polymers. And thank you very much for for joining us today. If you have any questions, please ask at the end of the second presentation. Thank you.
Thank you very much for that excellent presentation, Vladimir. Yeah, as Vladimir mentioned, we will of course be having the Q&A session at the end of the webinar. So if you do have any questions for Vladimir, then please do post them in the chat box, and then we'll get to them later in the session. For now, though, we'll move on to the second part, where we focus on the platform Nano and how it can help you with your research efforts. So I'd like to hand you over to our host for this session, Dr. Pranoti Kshirsagar. Pranoti is a product manager for nanoscience and technology at Springer Nature. Pranoti stepped into the world of science with a bachelor's in metallurgical and materials science engineering. She then earned a master's of materials science with a successful thesis at the Max Planck Institute in Germany. Pranoti followed this with a PhD for her thesis titled Carbon-Based Transparent Microelectrodes for Simultaneous Electrophysiology and Optical Investigation. In 2019, Pranoti received a doctorate in applied physics from the University of Tübingen in Germany. So Pranoti, over to you.
Thank you, Steve. Hi, everyone. Welcome to the second part of the session today. Thank you, Vladimir, for a wonderful presentation. And as he mentioned, please save your questions, or you can already type in your questions in the questions box. And after my presentation, then we'll get through all of your questions. So in the second part of today's session, what I'm going to tell you about is the Nano database, which is essentially a nature research solution. And here is the agenda that we are going to follow. Which is basically, I'll explain to you the idea behind the database, how it came to life, what does it offer you. Then we'll do a live demo by going to the URL nano.nature.com. I will give you some examples, use cases, how you can use the platform. We'll summarize then how Nature Nano helps you in detail. And then we'll get to your questions. So feel free to keep writing your questions in the questions box. Steve is keeping a very close eye on the questions box, and we'll try to cover as many of your queries as possible. All right, without further ado, let's begin with the idea behind the Nature Nano database. And for that, we need to zoom out a bit and look at the field as a whole, and look at how it is exploding, how it is growing. So as you can see from this graph in front of you, the number of research articles or peer-reviewed journal articles and patents are growing over the years. If we look at the last 10 years, and at the end of 2020, when we extend the x-axis here and put 2020, you will see that the articles are still growing, the patents are still growing, which is great, which is amazing for the researchers, for the research, for the field as well. As this means that you have a lot of information or a lot of literature to refer to when you're going about your research activities, be it planning your experiment, writing your thesis, writing your research proposal, whatever kind of research activity you are doing. However, this growth in the literature does come with some downsides, and I've tried to summarize or narrow down the challenges that are faced by the nanoscientists across the world. On this slide, 4 points, and this is also coming from my experience as a researcher, as a nano researcher for about 8 years. The problems that I faced, or the challenges that I faced, let's go through it one by one. So starting with the noisy results, what does that mean? So it basically means that when you type in whichever search tool you use, whichever advanced research engine you use, whenever you type in your keywords, the number of results that are coming up are plenty. And which also means that there are also a lot of irrelevant search results, which is essentially quote unquote noise that you don't really want to be bothered about or bothered by. And this again also ties very well together with the data validation, which is the second pain point, which is that because you have so many relevant search results, and even if you do have relevant search results, what you have to do is that you have to manually fact check by reading the original source to assess it for yourself, if this is really valid for your research, if this data is valid for your research. So that is the second pain point. Then, of course, the scattered information. It's a no-brainer that with the number of papers that are published or number of patents that are being granted, that the peer-reviewed scientific articles are scattered between journal to journals and from patent office to patent office. And all of this definitely then leads to the fourth pain point, which is the missing list. Which essentially means that there is no one place where all the information about the field or about nanomaterials, for example, can be found, such as how to synthesize nanomaterials, how to characterize them, the biological effects, so everything about nanomaterials. There is no single list which exists, which the researchers like you can go to whenever you are looking for any kind of information. So these four main pain points, and there are many more downsides to the growing nanoscience literature. However, to address these four pain points, Nature Research essentially launched this research solution, which is Nano, so nano.nature.com. And this is the first non-journal product to come out of the brilliant minds at Nature Research. And that's also one of the many reasons why we are very proud of it. And it's also being used by researchers all around the world. Heavily, extensively, it's been used, and we hear really nice words, kind words, that how much Nano is helping the scientists like you in going about your research. So what is Nano? What does it offer? So to begin with, all the information that you will find on Nano, which is nano.nature.com, that's the URL, all this information is coming from trusted sources, and this is a curated content which is available to you at your fingertips. And Nano basically was made with the idea of bringing all the information about nanoscience and technology under one umbrella. And the content can be understood in three sections, so summaries, articles, patents. And for all the three different categories that you see on the screens in front of you, we heavily use the artificial intelligence. And in some cases, we also combine it with the manual intelligence. And we can talk more about it. If you do have questions, happy to go into more details. However, for the time being, I would like to walk you through and tell you about the three different contents you see in front of you, a little bit about the content. So a nanomaterial summary is basically everything about a nanomaterial, starting from how to synthesize it, how to characterize it, applications of it. So whatever has been reported about a nanomaterial in a scientific paper or a patent, all this information is extracted manually and is inputted in the platform. And I'll show you how it looks like when we go to the platform itself. That's the summaries. First category is the summaries. Second is the articles. Now, in case of articles, we heavily use the AI. We cover articles from Springer and Nature, of course, which are relevant for the field of nanoscience. And in addition to that, we also cover articles from other publishing houses as well. Because remember, the idea is to bring all information in one place so that all of you have access to everything about the field in one place on one platform. And we heavily use AI specifically for articles, and there are two advantages of doing this. And I'll go over those advantages when we go to the platform itself, when we'll do the live demo of the platform. The third category is the nanotechnology patents. Now, the big number of 25 million is because we cover patents from over 95 patent offices all around the world. And in this case, also, we heavily rely, or we heavily use the AI, which then, similar to the articles, goes through the full text of the patents, identifies the most important section, which is the claims section, translates the first 5 claims in English, and that's what you have access to on nano.nature.com. All right, let's go to the platform. How does it look like? So I'll just zoom in a little bit. The content that I was referring to is down here. Up here next to the logo, we have the search bar. Now in the search bar, you can put any keywords that you think are relevant for your research, as many keywords as you like, be it a nanomaterial, a property, characterization technique, application, biological system, anything that is relevant for your research, you can type that in. I'm going to type in a very simple keyword, graphene, just as an example, just to show you how powerful the platform is and what it can offer you. On the left, you have the filters, which you can click as many filters as you like to narrow down the search results that you see on the right. And now what I do want to show you is how does this nanomaterial summary look like. So now I'm going to click on graphene up here, and where it essentially takes me to is the graphene summary. So all the information that you will see below has been manually extracted from over 6,700 articles and over 100 patents. Okay, all this information has been extracted by our team of more than 70 people whose daily job is to read these articles, read these patents, take out the information and input it in the system. How does the summary look like? Let's scroll down. For example, in case of properties, either you can scroll down to find the property that you are interested in, or you can just type the property in the search bar here. So let's say I'm interested in emission of graphene, for example. So you can just type that in, and all the papers that are reporting about emission of graphene will just show up. In addition to that, what we also extract is if the dimensions of the nanomaterial are reported in a particular paper, then you will also see the dimensions here. For example, over here, you see the size of graphene in this case is 19 nanometers. And if you think this is something which is relevant for you, interesting for you, and you want to read more about it, you can simply click on the hyperlink in the source column, and this will take you to the original article where this information has been reported or where this information has been extracted from. Similar tables will show up when you go from properties to applications to characterization, biological effects. In case of preparation, it looks slightly different, where you can compare between the different preparation methods and then make up your mind which are the papers that you want to focus on. And by simply clicking on the source, you will be redirected to the original article where this information can be found. So that's the nanomaterial summaries. Now let's go to the article section. And before we go to the article section, or while we do go to the article section, what I'm going to do is I'm going to add another keyword here. So let's say thermoelectrics, just as an example. Let's see what comes up. So basically, again, the filters on the left, so you can filter the results based on the publisher, the journal, the publication year. And I promised to tell you 2 main advantages of using the Nano database as it heavily uses the artificial intelligence. And the first advantage is that, as I mentioned, AI goes through the full text of all of these papers. And if the keyword that you put in the search bar here on other platforms is not part of the title of a particular paper or particular article, then that particular scientific article will not even show up in the search results. And even if it does show up, it will be very, very far down. So this way, what happens is that you miss out on articles even if they are relevant for your research. So by using Nano, you do not miss out on any of the articles just because your keywords are not part of the title. That's the first advantage. The second advantage is a customized summary. Now, what's a customized summary? Everything you see in front of this article discusses, which I've highlighted in blue here on the screens in front of you. Everything you see here, this is a dynamic summary created for every article based on the keywords that you type in the search bar here. And of course, this summary is different for every article because every article is talking about something different. It's very unique. So this basically gives you an overview or a sneak peek into the article before deciding which articles to actually focus on, which articles to actually read yourself. So those are the two main advantages of using Nano when you're going about your literature review. Now let's go quickly to the patents section. How does that look like? Similar to the summaries and the articles, the filters are on the left here: country of assignee, filing year, patent office. You can use as many filters as you like. And in addition to the title of the patent and the other details about the patent, the AI, again, goes through the full text of the patent and translates the first 5 claims, which you can simply skim through just by clicking next here or previous here. And if you're not convinced, you can just hide the claims, move on to the next one, evaluate the claims yourself, and then make up your mind which patents to read. And for example, the second patent is something that is interesting for you. You can just simply click on the title and you will be redirected to the original text if it is available. So that's what the Nano database is, made with the idea of bringing all the information about the nanoscience technology field in one place. And I'm going to summarize the advantages real quick for you so that you understand how Nano can help you when you are going about your research. So starting with the nanomaterial summaries, all the information is available at your fingertips, which saves you a lot of time. In case of articles, you do not miss out on any articles, and the customized summary allows you to have a quick overview of the particular article before going into the details of it. And in case of you jump over the language barrier because the claims are translated in English, and now patents can be part of your literature review process. So with that, I would like to thank you all for joining this session, and now more than happy to answer any questions you might have. Feel free to type your questions in the questions box, or also raise your virtual hand if you would like to speak to us. So thank you.
Great, thank you, Pranoti, for that excellent presentation again. As Pranoti mentioned, now's the time for the questions, so please do type them into the questions box. And also, if you don't have a specific question, feel free to just type in your area of interest. If we've got time, your area of research, if we've got time, we'll come to that, and it could be that Pranoti maybe even can show you some of the things that you could do within your area of research on the Nano database. But we do have some questions that have come in. Firstly, there's been a few questions just asking about whether there'll be a certificate from this session, and I can confirm that yes, tomorrow we'll be sending out an email. Have a look in your inbox for something from the database group at Springer Nature. That will include both a copy of the certificate for attending the session and a recording of this session as well. So please do keep an eye out for that. We've also then had some questions that have come in specifically for Vladimir. So firstly, for Vladimir, a question from Prasanth. What should be proportional gain and integral gain for a good image?
Okay, that's actually a very good question. Thank you for asking that. Quite often, high-resolution imaging for polymers is done in what is called a phase imaging. And when doing phase imaging, you would want to keep your integral, well, both integral and proportional gain a bit low to minimize basically noise from your topographic scanning. Those numbers, they largely depend on the system that you use, because different manufacturers use different conventions how those feedbacks are controlled. So as a general guidance, for topography, if you want to track topography, of course you need to up the gains to make sure you track it. But quite often for polymer imaging, for high-resolution polymer imaging, you want to look at the phase channel, and then you want probably to drop the gains a bit lower. How low, again, it would depend on the specific system. Then I could possibly tell you the numbers.
Excellent. Thank you for that, Vladimir. We've got a question here for Pranoti as well. So Pranoti, how often are articles added to the Nano database?
Yeah, so that's a very good question. So the articles, the data is updated on a regular basis. The articles are added every twice a week or thrice a week, depending on the load, and the patents the same thing. Whenever the patent is available online or is granted and the full text is available, you should be able to find it on the platform, or it will be part of the platform within 48 to 72 hours maximum. It does take a while for the nanomaterial summaries though, because those are created manually. So those might take a couple of weeks after the paper is available online. But yeah, in principle, the information or the data is added on a regular basis as quickly as possible. Thanks.
Great, thank you, Pranoti. We've got another question here for Vladimir. It comes in from Joyce. So, hi, Vladimir. Thanks for the great presentation. Could you tell us more about the sample preparation for the AFM characterization?
Right. Well, thank you very much, Joyce. Indeed, sample preparation is critical for AFM imaging. In terms of sample preparation for this particular presentation I gave today, there isn't any. It's literally a piece of a Teflon tape, and I can show you. That's what it is. You can literally buy it from your any local shop that sells it. You cut a small piece, as small as you want or as large as you want, and place it on a sample check of your AFM. So in that sense, there is no sample preparation for that particular sample that I showed today. But for other samples, indeed, the sample preparations could be quite tricky, and it is largely depends on what sample you want to image and what information you want to get from the sample. But for Teflon, it is remarkably easy system, and when you combine with a low noise level atomic force microscope like this system, you can get those results relatively quick and easy without any special preparation, really.
I do have a follow-up question on that. Can you reuse the tip when you are doing the AFM scans of this tape, or does it get dirty? It must get dirty, right?
It's actually a very good point. In general, yes, when you scan something with your probe, of course, occasionally you may pick up things, especially if you're scanning something that is loosely bound to the surface, or there's some contamination there, something you get that sort of problem. But the beauty of a Teflon, it's the material with the lowest adhesion that is known in nature. And that's why there's almost no contamination on top. The adhesion between the probe and the surface is very low, so not much really sticking to the probe. That's why for Teflon samples, you can reuse those probes for days and weeks, and especially when you use it on a system where it's like a really good force control of tip sample interaction, like on the next 20, the tip wear is really minimum, and for that type of sample, you can use that probe. Not sure how long for, but probably for many weeks, getting exactly the same results. But for other samples, it may be slightly different. Again, it's all sample dependent.
Absolutely. Yeah, thanks.
Great, thank you both. Pranoti, another question for you. How detailed are the summaries on the Nano platform?
Yeah, so we basically try to extract, that's a very good question actually. We basically try to extract as much information about the nanomaterial as possible. So its dimensions, it's the medium in which that property was evaluated, or the support system, if there is any. This is for the property section. Then for the biological systems, we basically, as much information has been given by the authors, we try to extract all of it or most of it. So it can be, we try to do it as detailed as possible so that you get to, once you read the summary, you can definitely decide if to read if this paper is worth your time, if you should really spend the time reading this paper or not, so that you can focus your energies properly. So yeah, we try to give them as much detail as available in the papers. All that will be part of the nanomaterial summary. Yeah.
Super, thank you, Pranoti. Another question for Vladimir here. What is the nano high resolution AFM in contact mode or in tapping mode? From Ali.
Sorry, Stan, could you please repeat?
Sure. So what is the nano high resolution AFM in contact mode or in tapping mode?
I'm not sure I quite get it, but
I think Ali means that which imaging is better. Where do you get high resolution? Is it contact mode or tapping mode? I think that's what Ali means.
Oh, okay. Well, in that case, that in principle, if we're talking theoretically, the best possible resolution you should get in contact mode, where if say you have ideal probe with the atom right at the apex of your probe, and that single atom touches your surface with the extremely low force, then in that ideal situation, you will get the best possible image. But we live in a very real world, and you will never get a single atom or molecule sticking at the end of your apex. So it was some kind of structure there. From experimental perspective, because I'm more like an experimentalist rather than a theoretician, from what I can see, the best resolution that you can get in the ambient imaging, that can be achieved in tapping mode at the moment. It may change, and depends on how manufacturers change the way they build microscopes, but at the moment, tapping mode is the highest resolution mode amongst most imaging mode for ambient atomic force microscopy.
Great, thank you.
Answers the question.
We've actually got another question from Ali as well. So he's also asked, what is the best mode of AFM for imaging contact mode or non-contact mode?
Again, what is the best mode? That largely depends on your sample and what you're trying to achieve. PARC has pioneered the use of non-contact mode, which is really great when you want to get your images, like good quality images, very quickly with the minimum tip wear. And even for very challenging and demanding samples, like various hard surfaces, that imaging mode provides you with almost no or extremely minimum tip wear, and you can generate hundreds, if not, I believe some people generated thousands of images with absolutely no damage to the probe. But then again, on any modern microscope, you can use any imaging mode that you wish to. That really depends on your samples and what information you want to get. I don't think there is such a way like what's the best imaging mode. Each imaging mode is good for certain things, for certain applications. As I showed today, sort of high eigenmode version of tapping mode is really good for high resolution imaging. If you want to see very small structures like molecules, and in some samples we can see atoms and so on, then that's your perfect imaging mode. Is that the perfect imaging mode for all samples and all situations? Well, probably no. And you might want to use non-contact mode for other situations. But again, it's as usual, you have a choice of imaging modes to use for your particular samples. So it's always like the question should be, what is the best imaging mode for that type of sample to get that type of information? And then you can say, okay, well, that's your best option, really.
Great, thank you for that, Vladimir. And Ali's actually dropped a note to say thank you for the answers. So I think you've answered those well. Thank you.
You're welcome, Ali.
Pranoti, we've got another question for you. Could you tell us when Nano was launched? And it's a double-pronged question, actually. When was Nano launched, and how can somebody get access to it?
Yeah, that's yeah. Yeah, so I'm smiling because we recently celebrated the 4th anniversary of Nano. So it was launched mid-year 2016. So it's about 4.5 years old, somewhere close to that. And the way you can get access to it is check if your institution has subscribed to the Nano database. Make sure that you are in the IP range of your institution, and then you can just simply go to nano.nature.com, access the platform through your library, either with VPN or Shibboleth or whichever off-campus or remote access method your institution is using. And if your institution does not have access and you do want to use the platform, then drop us a note and we'll try to make sure that you get the access. Leave it with us. Just let us know that you are interested, and then we'll get you the access to the Nano database. Yeah.
Right, thank you, Pranoti. Another couple of questions for Vladimir. Firstly, one from Natalie. She says, thank you, Vladimir, for your presentation. Is it possible to image in liquid media using eigenmode?
Right, Natalie, thank you. Thank you actually for raising a quite important question here. Indeed, you can use that approach, high eigenmode approach, in almost any media that is compatible with your microscope and your probe. So, you can certainly use all high modes of the cantilever and water, and that's something that I used, and you can get similar results. And again, because you're using a higher frequency and the Q factor, the cantilever doesn't really scale up as quickly as the frequency does, you can actually scan faster again. So yes, that technique is not limited to just ambient imaging, but it could be applied equally to any other media. Again, my usual answer: just give it a go, try. That's the best way you can do with any microscopic technique. Just give it a try, and it should work.
Right. We've got another question here as well from Pinchu. How do you avoid the artifacts in AFM imaging? What are the experimental difficulties?
Indeed, that's quite an important question. Artifacts, there's a whole range of those artifacts that people often aware or some unaware of. One critical step is to use a very gentle tip approach, and for instance, on part systems, there is a very specific software that controls your engage process, how quickly and how gently the probe engages your sample, and that helps you first to maintain the sharpness of your probe, and by maintaining the sharpness of your probe, you avoid having most common artifacts like double tip, for instance. That is a very common artifact. So engage, the way you engage and the way it's implemented on the microscope, that is critical. And next ones and the similar park platforms, they did a great job in terms of very exquisite control, how you can approach a sample without damaging your probe. That is quite unique technology here on the next one and the next 10 series of AFMs. Again, I guess like in any microscopy, it's your attentiveness and looking at the images and the images that you collect. You should always question yourself whether the structure that you see is real or not. That is the question you should always ask yourself, because sometimes microscope can just generate images that they look pretty, but they mean nothing. And then you can apply very simple techniques like scaling up your image. So increasing the scan size and see whether the feature scales up, rotating the scan direction and see whether the feature actually rotates or not. So these are kind of very basic but surprisingly powerful techniques that can help you to eliminate very common and standard artifacts in any AFM or STM imaging. So
excellent.
That answers that. Thank you.
Yeah, thank you very much, Vladimir, for that answer. We have got to the end of the session, but we've got a couple more questions. So what I suggest we do is we just carry on for a few more minutes. We answer the questions that are outstanding. If people do need to drop off the call now, that's absolutely fine. Like I said before, the session is being recorded, so you'll see all these when the recording comes through tomorrow. So we'll get to the last couple of questions. Firstly, a question for Vladimir from Tamizi. Thank you, Vladimir, for the excellent presentation. Is it possible to follow the formation of PTFE from precursor in solution phase to solid phase by eigenmode?
Yes, indeed. One of the beauties of the AFM, you can follow the dynamics in the real space in the real time. Of course, when we say real-time dynamics, if things happen on an extremely small time scale, then any AFM would probably be a bit disadvantaged, because AFM is really designed to look at the processes that happen, say, on a minute or at least tens of second scales. If you're skillful enough, then you can follow that. If something happens on a much faster, on the millisecond scale, that might be slightly trickier to follow. It's still doable, and people do that kind of experiments. But the actual setup would involve not just saying, okay, we're going to use the high eigenmode technique, something else, but that would involve the actual sample preparation. And that brings us to the very first question of how to prepare a sample, and then how to set the whole experiment up to look at the formation and crystallization of those molecules. And that will be the key to the success. So that kind of experiments, they're looking at the dynamics. So you have a couple of, or actually a few components that you have to get right. It's, of course, you need to get a microscope right. The microscope has a low noise. You have to get the cantilever that you want to use, and you know that it will deliver good results. And critically, it's the sample and the sample setup that you need to master. And then those three components glued with your expertise and experience, that's really a recipe for a success in that type of experiment. I know it's kind of vague answer, but the rule is very simple. So the more you want to get from your sample, the more time you need to spend setting up your experiments, and it's quite often it will eventually come down to the sample prep and the actual design of the experiment rather than the instrument part of it, because instruments they can do whatever you throw onto the tip. There's no issue with that. It's the way you design your own experiment and your own sample. That's where the problem often is.
Great, thank you for that again, Vladimir.
Right.
Another question for you from Prashanth. How do proportional gain and integral gain contribute to an image?
Again, when doing phase imaging, and quite often high resolution is done with phase imaging, you try to use relatively low gains to minimize effects from the noise from topography, basically. So that will vary from system to system how you control those gains, and unfortunately it's something that lacks any proper theory. It's more like you need to observe and be very patient in how you adjust them, those gains to get in. They will be basically specific to the instrument that you use. From whatever manufacturer you may use that instrument. So there is no any particular numbers or range of numbers that you may use. That will be very much depending on the instrument, your sample, scan size, scan speed, how quickly you scan, and that will determine those gain parameters. So sorry, I can't be more specific, really. It kind of gives you the direction where to go, really.
Excellent. Thank you for that, Vladimir. That's the last of the questions that we have on the list right now. Just in case there are any more to come in, I'll just cover one more housekeeping point briefly, just while we see if any other further questions come in. Just to let you all know that when the session finishes today, you will be redirected to a short survey, just a few questions, and it'll only take just a few seconds to fill that in. We would ask that you do that, if you could just take a few seconds to do that, just because it will give us a bit of feedback on how today's session's gone and any things you'd like to see us covering in future sessions. Ultimately, it will help us to improve these going forward and cover the sort of subjects that you're looking to hear about, basically. So yeah, we'd really appreciate it if you could just take the time to fill in those few questions that you'll see. For now, though, there are no more questions that have come in, so I would just like to say, firstly, a big thank you to our two presenters today, Vladimir and Pranoti. They both have done excellent presentations, and thanks in particular for the really in-depth answers you gave to all the questions that came in. We've seen a number of the people who asked questions have followed that up by saying thank you. They're really great answers, so really do appreciate that. So yeah, thank you to you guys, and also thank you, of course, to everyone who's tuned in today. We hope you found it useful and informative, and we look forward to welcoming you to more of these sessions in future. So thank you very much.